doing image analysis. The first day they arrive at grad school or whatever. This would be it. So now that we're 3 minutes away from the end of this workshop, which is that the single easiest way to misinterpret imaging data is to say, I see a significant blob here, I don't see a significant blob here, or this is brighter than that, therefore there's some difference. Even, I see a positive relationship here, I see a negative relationship here, therefore these things are clearly different. The bottom line on these comparisons is that although it is possible to sort of make these comparisons in a way that's not too misleading, if you can't put a p-value on it, if you can't put some sort of statistical value on it, some sort of estimate of reliability, it's not really a scientific observation. It's just a sort of off-the-cuff observation. And frequently these observations are very misleading in fMRI, and I would say in VLSM as well. It's been argued that if you were to run an fMRI, many fMRI studies with enough subjects and enough trials, thousands and thousands of each, that eventually the whole brain would light up. I don't know if that's entirely true, but the argument could be made that that many fMRI studies and certainly many VLSM studies are somewhere between dramatically and moderately underpowered. So when you see a difference between regions, it's important not to overinterpret it without some direct evidence. Now, I will say that as of this past week, I have learned how to calculate one type of intervoxel comparison, where if you have actually a simple t-test in two voxels, which can be recast as a correlation, there's a clever test for this. Even though, so far as I know, nobody else in imaging uses this test. A reviewer asked for it last week, so we now know what this test is. It's what we've decided it could be called the Hotelling-Williams test. It's actually pretty easy to carry out. So as long as you can pick two voxels and say, do these two voxels have an equally strong relationship with our dependent measure, that question can be answered. There are apparently methods for doing this in multiple regression as well, but they're very complicated and rely on resampling techniques. I don't know that they're that complicated. They're complicated to implement. And we certainly don't have implementations for imaging, so right now we can't do that. But I do think that a lot of this issue with left hemisphere, right hemisphere stuff does come down to understanding alternative explanations for the effect, which often is going to involve making eyeball comparisons that you shouldn't really be making. So it's exactly 5 o'clock according to my computer. Any questions?
I don't know. Nobody has those but I want to hear what you have to say in terms of the minimum subjects.
Oh yeah.
Kind of just in a nutshell.
Yeah. So this question I get more than any other question about VLSM, and I've given it a tremendous amount of thought, and I don't have a good answer for it. So there is no objective standard for it as far as I can tell. Depending on when you catch me, I might say 5. Chris Roden would usually say 10. But the real answer is that if our test statistics, if our t-statistics were really well behaved, no matter how many subjects you had in your groups, this wouldn't matter. The right answer would be 1. But they're not, and the reason they're not is because as I understand it, given my feeble understanding of statistics, is that when you have a t-test between two groups and one of the groups has 2 subjects in it, you don't get a good estimate of variance in that group. So that's actually more important if you're running a Welch's t-test, where you're trying to estimate the variance in each group independently, than when you're running a regular t-test. But nonetheless, people sort of, I think, rightly feel that a t-test with 2 subjects in one group, which is the minimum where you could numerically carry it out, doesn't make much sense. What I like to say to people is retreat to what you I don't know why I just assume everybody doing this is sort of a psychologist, but fill in the name of your preferred field of expertise. Is what would you do if this weren't imaging data? If you were going to carry out a t-test between 2 groups, given a medical intervention and it was the only test you're reporting in an article. Would you feel comfortable reporting it with 100 subjects in your control group and 2 in your experimental group, 2 in your injured group, whatever it is? And if the answer is no, then you probably shouldn't be reporting it for VLSM either. So it's not a very satisfying answer, but I think it at least pushes the problem back on the individual researcher in the sense of saying, if you don't have a problem, a solution for this in your work as a psychologist, then there's nothing special about VLSM that makes it a particular problem. Any more stuff? Questions for the other guys? This is the last session.
Do you have 2 words to say, 3 words about power mapping? Was there something new that you didn't talk about?
No, I thought when I put the slide up that I was going to sort of show how to go through power mapping. Our approach to power mapping, which I'm not going to say is ideal, but there's lots of other viable approaches. But what we described in our 2000, what year was it? 2007? What? Yeah, 2007 JSCN article. Is basically to sort of figure out what the corrections for multiple comparisons is going to be, and then calculate the power at each voxel, or not really at each voxel, but for each number of lesion patients, using some external tool. If you only have a maximum of 50 lesions, then you only have to calculate 50 power values. It's not that hard. At some point, I'll put power calculations in Voxbo, and it'll make it easier. And then just sort of map it onto the brain. It's a reasonably effective approach. Yeah, there's not that much to say about it. So I'm going to try to put together some tools that actually make it a little easier, because the approach I recommended before is laborious. But there is a feature in VBIM that makes it a little easier. To take values like that and map them onto a volume. Let me see if I can find that feature. Oh yeah, remap. Okay, so this remap feature lets you create a little file. The file has 2 columns. One has the number of lesions in the voxel. The second column has the power that you expect in that voxel. And then you create that file by running your little power calculation program. Takes you 20 minutes to go through all 40 values. And then, you write a bash script. It takes you 10 seconds. And then you use the remap option to actually remap your count map using this. So it takes you say something like this: VBIM count dash remap my little map.ref, and then write power map. And if my little map.ref existed, which of course it doesn't, you would get a really terrific power map. So that at least streamlines the process a little bit. I would, by the way, encourage anyone who's going to use Voxbo to learn at least a little bit about bash scripting. Bash is the shell that lets you type stuff and executes commands. And you can write little bash scripts to do all sorts of clever little things. Like, for example, you can say for file in star.voi do ls file done, and it iterates through the files and then lists them. That's not the most useful thing, but however, if instead of ls this were some complicated program that does something useful with the file, this is a much easier way to do it than typing that complicated command line 50 times or whatever and waiting for it to finish. So that's just a simple example of something you can do with bash scripting. But among other things, bash scripting is very helpful in remembering what you did and making sure you can repeat it easily. And in conclusion, I want to say that I'm going to have various slides, the text file used for this, and stuff. The cheat sheet that I've been promising everyone up on the Voxbo website pretty soon, which is, again, at this address, voxbo.org/VLSM. That actually just redirects you to a page on the wiki that I can never remember the name of. And I'll try to keep that page updated. The Voxbo website also does have general pages on VLSM where I'm going to try to keep, which I will try to keep updated with the latest stuff. And now, really in conclusion, what I will say is that Everything you've learned is now obsolete. Practice in VLSM analysis changes on an almost daily basis. So that's one of the reasons I would encourage paying attention to the mailing lists. But also, we learn new things about the analyses. So it's helpful it's important more important than in most areas to keep up with things. So so please do that. Is that it?